My name is Olivia Nabawanda from the Department of Mathematics, Makerere University, Kampala, Uganda. And I'm a PhD student at this university. My topic today is the sets of flattened partitions with forbidden patterns. And what I'm going to talk about actually forms a part of my PhD work, which has been submitted to a journal for peer review. I'm working under the supervision of Professor Fanja Raktondrajao from University of Nairobi, Madagascar, Professor Paul Vadalin from Stockholm University, Sweden, and Dr. Alex Samuel Wamnawa from Makerere University, Kampala. This will be the outline of my presentation. I'll begin with some definitions and background. I'll move to the motivation, the notation that I'm going to be using throughout my talk. Then I'll talk about three-letter avoiding flattened partitions. And these are in two cases. I'll first consider flattened partitions avoiding a single three-letter pattern. Then I'll look at flattened partitions avoiding a pair of three-letter patterns. And then I'll conclude my presentation. Okay. Let's begin with some of the definitions that will enable us to understand whatever I'm going to talk about. For a fixed positive integer, n, we shall denote the set with any elements by this. This is a standard notation. So wherever you see this, this will be representing a set with n elements. And a permutation sigma will be represented as a word, sigma 1, sigma 2 up to sigma n, because we are looking at a permutation of length n. And then about the pattern, I will say that a permutation sigma contains a pattern tau if we have a subword in sigma, which is order isomorphic to this pattern. And if sigma does not contain a subword that is order isomorphic this pattern, then we say that sigma is tau avoiding. And that is what we mean by the forbidden pattern. In that case, we shall be having a forbidden pattern. And a subword in a permutation can consist of consecutive elements. The elements can be consecutive or non-consecutive. For example, if you look at this permutation of length 7, this permutation contains a pattern 231 because we have a subword 561. And when we standardize this subword, it gives us this pattern 231. So it contains that pattern. And on the other hand, when you look at this permutation, still it's of length 7. This permutation does not have a pattern 231. So in this case, we say that this permutation is 231 avoiding. So the forbidden pattern in this case is 231 in this example.
Sorry, please. I don't understand what you mean by pattern 231. So I have to add my question now so I can follow the rest of the talk. What do you mean by contain the pattern 231? I didn't understand.
That is now the definition of a pattern. We say that a permutation has a certain pattern if we have a subword in that permutation sigma. Like in this case, in this permutation, we have a subword 561. And when you try to write this 561 in standard form we mean that the smallest element takes on 1, the second smallest takes on 2, and so on. So in this case, if you look at 561, 1 is the smallest, so it will take on 1. 5 is the second smallest, it will take on 2, and 6 is the biggest, so it will take on 3. So 561 is now the 231 pattern. So we say that this permutation contains pattern 231. And when you look at the second permutation, it does not contain a pattern 231. These are different permutations. So this second permutation, which does not contain a pattern 231, we say that it is 231 avoiding. Okay. The next definition is a set partition, because I will need it somewhere. So given a non-empty finite set, which I'm denoting by S, a set partition P of this set is just a collection of disjoint non-empty subsets, which I'm denoting by B1, B2 up to Bk of S, such that the union of those subsets gives me the finite set S. And in most cases, a partition P is always denoted, is always written in this form. We always have blocks separated by this vertical bar. I'll call it a bar. So this is how we shall denote a partition of a set. Now let's move to a flattened partition, which is the main point of focus of this in this presentation. What is a flattened partition? A flattened partition is also a permutation, which is obtained, one, by writing the elements in the different blocks of P. P is the set partition, which I've just defined. So we write the different elements of P as increasing subsequences. And then we arrange the blocks in order of increasing first entries. So the block with the smallest first entry will come first, block with the second smallest first entry will come next, and so on, depending on the number of blocks that you have. And then finally, we remove these marks here, enclosing the different blocks of P. For example, we have a partition P given by this. This is from a set with 7 elements. And in this partition, we are having the different blocks. So as per the definition, we are now writing the elements in the different blocks as increasing subsequences. So the 261 will now become 126. 7-4 will become 4-7, 3-5, that one is already increasing, so we shall maintain it. And then we arrange the blocks in order of increasing first entries. So in this case, the first block starts with 1, that is okay, because it's the smallest. The second block is starts with 4, and the third block starts with 3. Since 3 is less than 4, so this third block is going to take up the second place, so that we end up with this arrangement. And then if we remove these marks enclosing the different blocks, we have this resulting permutation. And this is what I'm calling a flattened partition. And from that definition, it's clear that each flattened partition therefore starts with integer 1. So all flattened partitions are actually subsets of permutations. However, different set partitions can have the same resulting flattened partition. For example, if you look at these partitions from a set with 3 elements, and then this partition and this one, when we want to get the resulting flattened partition, that is doing away with these vertical marks, we are in all these 3 cases, we are going to end up with a flattened partition 1, 2, 3. And it's not difficult to identify a partition which is not flattened. For example, when you look at this flattened partition, it's not flattened, because when you consider, you suppose that the vertical bars which are enclosing the different blocks are there. In the first block, we shall have 1, 4, which is increasing, but in the second block, we have 3, 2, which is not an increasing sequence. So this is not flattened. And 1, 3, 4, 2 is a flattened partition. And where does this flattening notation come from? The notion flattened was introduced by David Callan in 2009. And this flatten is a command from Mathematica where it acts by getting different lists of sets and then writes them as a single list. So that's why we are having a situation of maybe in this case, 1, 2, that's a different list, and then 3. But with the flattening command, we end up with just a single list. So that's where this notion was borrowed from and was introduced by Callan. And the aim of my study is to investigate the number of distinct flattened partitions, avoiding patterns of length 3. And we have several counting sequences that result. For example, the Catalan numbers, I'm sure you've heard about them, powers of 2 Fibonacci numbers and Motzkin numbers. These are some of the sequences that we're able to come up with. Then I also need this definition of a run. A run in a permutation is also a subword of this form where sigma I up to sigma I plus P are ascents in a permutation, and then the sigma I plus P plus 1 is not an ascent, it's actually a descent. For example, if you consider a flattened partition pi given by this, we are having 3 runs, the first run being 1, 3, 9, 2, 7, 8, the second, and then 4, 5, 6, the third run. And when you look at the first run, 1 is an ascent, 3 is also an ascent, and 9 is not. So that is this form, sigma I up to sigma I plus P. And also, given a partition P from a set of 4 elements, you can see that P has 2 blocks. But if you are to look at this partition in the sense of a run, then in that case, we shall only have one block, because when you draw with this vertical bar, we just have one increasing subsequence. So this, I just put it to show you that blocks and runs are not necessarily the same. So why are we studying these patterns, pattern avoiding, permutations avoiding certain patterns? Studying patterns provides a convenient way for describing various combinatorial objects. For example, we have lattices like the Motzkin paths, Dyke paths, labeled trees. It can be sometimes frustrating and cumbersome to study these on their own, and these permutations avoiding certain patterns can come in and maybe give us a better way to understand such structures. And the reason as to why we relate certain combinatorial structures or objects to permutations avoiding certain patterns is basically to find bijections between the permutations avoiding a certain pattern and the different combinatorial structures. Okay, let's move to the notation that I'm going to be using. As in the definitions, tau would denote a single 3-letter pattern. And because we are looking at a pattern of length 3, that means you are basically considering a set from the symmetric group S3. And we have 6 such elements from that group. Then S n tau would denote the set of all permutations over n, avoiding a pattern tau. And then, since we've said that flattened partitions are a subset of all permutations, then I'll have this notation f n tau, which is a subset of S n tau, to denote the set of tau avoiding flattened partitions over n. And finally, Fn tau 1, tau 2. In this case, we are having 2 patterns. So this notation would denote the set of flattened partitions avoiding a pair of 2 patterns of length 3. Now, let's begin by looking at avoidance of a single pattern of length 3. We have 6 of such patterns, and we are counting the flattened partitions avoiding these patterns. These are some of the few values for each of the sequences that I was able to get, and these values were computed through a Python code that I wrote. So as you can see, for example, for the pattern 2, 1, 3, the resulting counting sequences are these are powers of 2. And then for 3, 1, 2, we are still having a sequence of powers of 2. So that suggests maybe a possible bijection between flattened partitions avoiding this pattern and avoiding 3, 1, 2. Then you have other sequences like for 3, 2, 1, that is a Catalan, these are Catalan numbers. So these are the first few values that we are able to get for each pattern. Now I'll begin by looking at flattened partitions avoiding pattern 1, 2, 3 and pattern 1, 3, 2. I'm putting these ones on the same slide because they are not so long and not so complicated. So for the pattern 1, 2, 3, we actually have a trivial counting sequence. As you can see, for n greater than or equal to 4, we don't have a flattened partition which avoids pattern 1, 2, 3. And in fact, the only potential candidate, because we've said that all flattened partitions start with integer 1. So maybe we would say that this permutation 1, 4, 3, 2, maybe it avoids a pattern 1, 2, 3. But again, this is not a flattened partition. So for n greater than or equal to 4, we have 0 flattened partitions, which are 1, 2, 3, avoiding. And for the 1, 3, 2 avoiding, it's an easy exercise to show that the only permutation, the only flattened partition which avoids this pattern is the identity. The rest contain the pattern 1, 2, 3. Okay, now as you've all seen from that table, we saw that 2, 1, 3 avoiding flattened partitions and 3, 1, 2 avoiding flattened partitions are both counted by the same sequence, which is a power of 2. That's why I'm considering them together. And we have an interesting property for 2, 1, 3 avoiding flattened partition, as seen in this proposition, that for any positive integer n greater than or equal to 1, the number of 2, 1, 3 avoiding flattened partition, rather a flattened partition that avoids pattern 2, 1, 3 has n at the end of its first run. And suppose n is not in the first run. If n is not in the first run, then it can be, say, in the second run, third run, and so on, depending on the number of runs that flattened partition has. And by definition of a flattened partition, so that means, looking at this example, this from 1 up to B, that will be the first run, and then A is the first element in the second run, and N can be anywhere, either in the second run or third run, and so on. So since we are looking at a flattened partition and the ordering that I talked about in the definition, it is clear that this integer B is greater than A. And so we end up having BAN, which is a 213 pattern. So, and this is a contradiction. So to avoid this, N for a 213 avoiding flattened partition has to be in the first run. Then we have a theorem here, and that is about the cardinalities of these two sets, 213 avoiding and 312 avoiding. We are saying that in the theorem that these two sets have the same size for n greater than or equal to 3. And we do this because there are two sets with the same size, then that suggests a possible bijection between them. So I give a bijection between those two sets. I'll not go into the details of the proofs, but I'll just give the main ideas in the bijection. One is the fact that a 312 avoiding flattened partition starts with a subword 1, 2, or 1, 3. And if we interchange integers 2 and 3 in a 312 avoiding flattened partition, that flattened partition will still remain 312 avoiding. So that interchange preserves the avoidance property. And also, we construct a map F from 312 avoiding flattened partition to a 213 avoiding flattened partition by a suitable switching of 2 and 3. And then finally, we also make use of this last idea that a 312 avoiding flattened partition contains pattern 213 if and only if the resulting 213 avoiding flattened partition under this map contains a pattern 312. So these basically are the main ideas in the proof of the bijection in the previous theorem. Okay. Now, since we've said that these two sets have the same cardinality, then in this theorem, we try to give the closed form of the formula that gives us the size of these two sets. And we have that for any integer n greater than or equal to, the cardinality of those two sets is 2 to the power n minus 1 with those initial conditions. And the proof of this is based on induction and the property of 312 avoiding flattened partitions, that a 312 avoiding flattened partition either starts with the subword 1, 2 or 1, 3. Basically, that's the idea in the proof of that theorem. Okay, now I move to the next set of 3-letter avoiding flattened partition, and that is the set of flattened partitions avoiding pattern 3 to 1. And what we came up with, what we found out, was that these flattened partitions are counted by the Catalan number Cn minus 1 with this initial condition. And the proof of this theorem is based on the work of Donald North in 2014, and that is given this reference 1. Catalan numbers are well known, and they are given by this formula, 1 over n plus 1 to n choose n for all n greater than or equal to 0. And in fact, after the Fibonacci sequence, Catalan numbers are the second most famous and sequences emerging in different branches of mathematics like combinatorics, algebra, geometry, and many others. So we also came across the Catalan numbers when we are looking at this set. So Donald North, in his work, proved that the number of 231 avoiding permutations, these are permutations and not flattened partitions, are counted by the Catalan number. And we are also coming across the Catalan number when we are looking at 321 avoiding flattened partitions. So that means to prove the fact that 321 avoiding flattened partitions are counted by the Catalan number, we do so by giving a bijection between these two sets. And actually the bijection was between the set of flattened partitions, length n, and permutations avoiding pattern 231 over n minus 1. And we also made use of the property that a 321 avoiding flattened partition contains a pattern 231 if and only if the resulting 231 avoiding permutation under this mapping, under this bijection, contains the pattern 321. This was one of the ideas that we used on top of North's work in proving that 321 avoiding flattened partitions are counted by the Catalan number. Okay, now we look at the 231 avoiding flattened partitions, and I begin here with a property of these flattened partitions in this proposition. We have that for any positive integer n, and pi, a 231 avoiding flattened partition of length n, there exists an integer k, k between 2 and n, such that the following are true. 1, pi of I is less than k, for I, if I is less than k, pi of k is n, and pi of I is greater or equal to k if I is greater than k. I'll use an example to show you what I mean here. So we have pi given by this, a 231 avoiding flattened partition of length 7. Then we say that pi is of this form with n, and n in this case is 7. So it means that on the left of n, we have a subword, and on the right of n, we also have a subword. So looking at this pi, we have that pi of 4, that is, pi of 4 is 7. As you can see, 7 is in the 4th position, and pi of I is less than 4 for all I less than 4. You can see from this subword on the left of 7, 132. All the pi i's here are less than 4, and pi of I is greater or equal to 4 for if I is greater than 4. And this is a property unique to all 231 avoiding flattened partitions. And we use this property to prove the next theorem. In the next theorem, we have that the number of 231 avoiding flattened partitions is given by this expression on the right-hand side. And this is based on the fact that for a 231 avoiding flattened partition, the subword on the left of n and the subword on the right of n, those subwords are themselves 231 avoiding. So we base on that to conclude that therefore all 231 avoiding flattened partitions are counted by this with these initial conditions. Okay. Now I have another definition here, which I think I'm finding it because I'll need it somewhere. That is a Moskine permutation. In his work, Mansour and colleagues defined a Moskine permutation as one which is both 132 and 1-23 avoiding. And by 123 avoiding, we mean that in sigma, the subword corresponding to integer 2 and 3 are adjacent in sigma. And the reason I'm bringing in the Moskine permutation is because they are related to Moskine paths and Dyke n paths. And I used this somewhere in proving some theorem that we are going to look at in a few minutes from now. Now, I've talked about a Moskine and a Dyke n path. What are they? A Moskine path is actually a lattice between 0, 0, as you can see from this diagram, up to n0 with up steps, which you are denoting by U, horizontal steps, which you are denoting by F, and down steps, which you are denoting by D. And this lattice never goes below the x-axis. And this is possible because of the fact that the number of up steps should not exceed, the number of down steps should not exceed the number of up steps. In that case, this lattice can never go below the x-axis. And that is the same case with a Dyke n path. It also never goes below the x-axis, though the only difference with a Dyke n path from a Moskine path is that for it, it only has up steps and down steps. Okay. We have another interesting result by Steele Mansour and his colleagues in their paper, where they proved that there is a bijection between the set of Moskine permutations and Moskine paths. And I've said that these 231 avoiding flattened partitions are connected to Moskine permutations. So that's why I'm now bringing in the Moskine paths and the Dyke n paths. How are they connected to 231 avoiding flattened partitions? Let's have this notation, Mn and Dn, to denote the set of Moskine paths, and Dn, the set of Dyke n paths. Then we have the following result, that the sets, this first set of flattened partitions, which are 231 avoiding, and the set of Moskine paths of length n-1 and Dyke 2n-1 have the same sizes. These three sets have the same size. And the idea in the proof is, first of all, to prove a bijection from 231 avoiding flattened partitions to Moskine permutations. And then since we already know from Mansour's work that there is a bijection between Moskine permutations and Moskine paths, in that case, the proof just comes out automatically if I use those ideas combined together. So how do we obtain a Moskine permutation from a 2-3-1 avoiding flattened partition? I'll do that in this example. We have pi, which is 2-3-1 avoiding and of length 8. To obtain the Moskine permutation, we delete the first integer, 1, and then reverse the order of the remaining elements. So we shall begin with 6, 5, 7, 4, 8, 2, 3, and then we write this in standard form. So the corresponding Moskine permutation for this 2-3-1 avoiding flattened partition will be this: 5, 4, 6, 3, 7, 1, 2. And the procedure for obtaining the Dyke end path and the Moskine path from now, a Moskine permutation is given and well described in Mansour's work. So because of the limited time that we have, I couldn't put the details of how to get the Dyke path from a Moskine permutation and then Moskine path. Okay. So in summary, we've been looking at flattened partitions avoiding a single pattern of length 3. These are the sequences that we were able to get. We have the Catalan numbers, we have the Moskine numbers, powers of 2, and then sequence of 1s. This trivial, this is where we had n greater than or equal to 4 being 0. There are no flattened partitions avoiding 1, 2, 3 for n greater than or equal to 4. Okay, now I'll move to the next part, and that is looking at the avoidance, looking at flattened partitions, avoiding a pair of patterns of length 3. From the symmetric group S3, we can obtain 15 pairs. And this is how they are distributed for these two patterns. We are having a sequence 1, 1, 2, 3, 5, and this is a sequence of Fibonacci numbers. And this one, sequence of 1s, that's trivial. Zeros for n greater than or equal to 4 for all these pairs. That's also not very interesting. And then for these 3 pairs, they are all giving us this sequence, which is a power of 2. And then this last pair, 2, 1, 3, 3, 1, 2, gives us a counting sequence, 1, 2, 3, and so on. And still, we obtain the first few values of these sequences through a Python code that we wrote. Okay, I'll begin with this pair, 2, 1, 3, 2, 3, 1, which we've said is counted by the Fibonacci number. Fibonacci numbers are in most cases the recurrence. When we are looking at the recurrence relation for the Fibonacci number, we look at the 2 previous steps. So that's the same principle that we're applying here. In order for us to construct flattened partitions avoiding these 2 pairs and having length n, we consider flattened partitions avoiding these pairs and having length n minus 1, and then those ones having length n minus 2. And for the case of length n minus 1, we can obtain a length n by inserting integer 1 at the beginning of a flattened partition of this length, and then we increase the remaining elements by 1. For example, we want to get a flattened partition avoiding these pairs of length 5 from this of length 4. So we shall insert 1 at the beginning of pi, and then we increase the remaining elements by 1 to get this, which is still 213 and 231 avoiding. And then for a length n minus 2, we insert a subword 1n at the beginning of this flattened partition, and then increase the remaining elements by 1. For example, we want to get a flattened partition of length 5 from this one of length 3. So we shall insert a subword 15 before this pi, and then increase each of the elements in pi by 1 to get 15 to 4, 3. So that's how we construct these flattened partitions, avoiding this pair. And we had two such pairs, which are counted by the Fibonacci number, and this is the second pair with the same initial conditions. And the idea in the proof is somehow the same for if you are constructing flattened partitions of length n from those of length n minus 1. We shall, in this case, still insert 1 before pi and then increase the remaining by 1. But when it comes to a flattened partition of length n minus 2, avoiding these two pairs, we shall insert now a subword 13 at the beginning, and to avoid having an occurrence of two similar numbers, then we shall just increase the integer 1 of the pi in this set by 1, and then the remaining entries in this pi, we increase them by 2. What do I mean? Let's look at this example. We want to construct a flattened partition of length n from length n minus 2, avoiding these two patterns. So we have 1, 3, 2. So when we insert the subword 1, 3, and then increase this 1 of pi by 1, so you have 1, 3, 2, and then we'll order the remaining, the 3, 2, which will give us 1, 3, 2, 5, 4. So this is another pair which gives us flattened partitions, which gives us a Fibonacci sequence. Okay, another pair, this is 2, 1, 3, 3, 1, 2, which gave us a counting sequence. This pair satisfies the number of flattened partitions avoiding this pair satisfies this recurrence relation, which when solved, we have this simple form n minus 1. So all flattened partitions avoiding these two patterns is given by simply n minus 1. And the final result is considering the pairs, these pairs, which gave us the counting sequence as a power of 2. And remember, when we are looking at 2, 1, 3 avoiding and 3, 1, 2 avoiding, we saw that those two sets are counted by a power of 2. So to prove this, we just constructed bijections between each of these sets and the set of flattened partitions avoiding a pattern 3, 1, 2. And this is the summary of the resulting sequences from avoidance of two pairs in flattened partitions. We have the Fibonacci sequence, powers of 2, these are the most interesting, and then the counting sequence. These are some of the references that I was able to put here that I used. And now I'll conclude that from so far that the few results that we have, there are many questions one can ask about these flattened partitions, avoiding those certain patterns and other structures in combinatorics or in mathematics in general, and the behavior of these structures. So I'm not yet done with research, I'm still working. So this is part of my current work and maybe for the future. I extend my sincere appreciation to SIDA Bilateral Research Program in collaboration with Makerere University for funding my research, and the leader of this project, Professor Mango from Makerere University, for leading us well and guiding us. And then I also thank my colleagues from the Combinatorial Research Studio, that is a group for combinatorics researchers in Africa and other parts of the world, for the weekly seminars that we always have. Thank you for listening.